Hello students and friends. In today's video I am going to discuss the topic which students find difficult to understand because it involves visualization, because the molecules are three-dimensional in shape but they have to be drawn on the paper only on 2 dimensions. So I assume that you already know that when carbon forms 4 single bonds, then those 4 single bonds are directed towards the corners of a tetrahedron, which looks like this. See, you can see that this is, and many times you might have already seen that this is the tetrahedral shape, where you have in the middle that is a carbon, and the 4 bonds which you see are going towards the 4 different corners of a tetrahedron. And this is how, when carbon form 4 bonds, this is the shape that you get. Now to draw this shape on paper is difficult because you can't show all the 3 dimensions. So we use the wedge and the dash diagram. So I'll show you what is meant by that. So when I hold this molecule in this way, as you can see, then you will find that the bond with the white and the bond with the black, this one, the bond with the, I'll hold it like this, yes. So see, the bond with the white and the bond with the black, they are in the same plane. And then you can see that the yellow, see, the yellow is coming towards me and red is going away from me, right? So the yellow is coming towards me, as you can see, the yellow is coming towards me and the red is going away from me, and the white and the black, they are in the same plane, right? The yellow is coming towards me and the red is going away from me. So to draw this diagram, the 2 bonds which are in the same plane, that is this, are drawn with the normal lines, and the bond which is coming forward, that is the yellow one, is drawn with a wedge, and the bond which is going behind me, that means away from me, that is the red one, is drawn with a dot. So I will show you exactly what is meant by that. So okay, so see this. So this is what we mean. See, you can see that this white and the black, they are in the same plane, and the red, that is coming towards the observer, and this dash is going, as you saw, the yellow was going away. So this is the way we represent, that is known as the wedge and the dash structure. Okay, now the point is that when we will now we can actually rotate this molecule, right? We can rotate this molecule. So if we rotate this molecule, then also it's going to be the same molecule, but it will look different. So see now, this as you saw, that the white and the black, they are in the same plane. The red is going away and the yellow is coming towards me. But when I rotate it, see, then what happens is that now what you find is that, see, now you find that the yellow, see, the yellow and the white are in the same plane, and then what is happening is the black, the red is coming towards me and the black is going away from me. So yet it is the same molecule because I have just rotated this molecule. So now its wedge and the dash diagram would be different. So but it's the same molecule, right? It's the same molecule. So that's what I'm going to show you just now. That now see, right? So see this. See, now it's the same molecule, but now see, you have got the white and the yellow. So if the white and yellow are in the same plane, then the black goes here and the black goes here and the red goes here. So if you look at this initial diagram where you had the white and the black in the same plane. So red was pointing towards the observer and yellow was going behind. Now I have rotated it so that the yellow is now here. So yellow comes here, so black goes here in place of red, and red goes here in place of yellow, and this is the new shape which you get. But this is equivalent to this one, it's not different. In the same way, if I further rotate the molecule so that the red goes here, so yellow goes here and the black goes here, but yet it is the same molecule which has already been rotated. So 1, 2 and 3 structures that I have drawn are equivalent. But let us suppose that we come across a structure in which white and black are occupying the same positions as you saw here, but we have interchanged the red and the yellow. See, we have interchanged the red and the yellow. That means we have just made one change, right? So this is non-equivalent. This is non-equivalent because that means it is not the same molecule. It cannot happen that in one structure the white and black are in the same plane, in another structure also white and black are in the same plane, but in one structure yellow is going behind, red is coming forward, but in another structure you have interchanged, red is going behind and yellow is coming forward. It cannot happen. It cannot happen. So it means that these two structures that I have drawn 1 and 4, they are non-equivalent. So they are non-equivalent, that means they are not the same but they are different. So in fact they could be enantiomers, that means they could be the mirror images, right? And if you again go to suppose now let us say that we have the white and the black and the yellow and the red, right? So once again if we rotate it, then we bring yellow here, so the black goes here and the red goes here. Now they are equivalent, right? And now what I'll tell you is what is you have to understand. Sometimes we use something like Fischer projection. So let me tell you about Fischer projection. So now see, when we look at this molecule, and then we can actually you know, rotate the molecule in such a way that you can see that two bonds are facing you. Actually if you see, then these two, the red and the black, the red and the black, see this, the red and the black, they are black and the red, they appear in this picture to be you know, you can clearly see that they are pointing away from me, and the yellow and the white, see the yellow and the white, see I'll hold it from here, then you can see that the yellow and the white are towards me and the black and red are away from me. So if you draw like this, then we get what is called as a Fischer structure, and I'm going to show you that. So what you will see here is that, see now the vertical line shows that these are the vertical line shows that the bonds are away from the observer, as you saw the two bonds would be away from the observer and other two bonds would be towards the observer. So the horizontal line shows the horizontal line shows the bonds which are towards the observer, and the vertical line shows the bonds which are away from the observer. So in this way a three-dimensional structure can be converted into a two-dimensional structure, and that is called as a Fischer projection. Hope you understood the introduction to the stereo chemistry about drawing the wedge and the dash structures, and also converting those structures to the Fischer projection. So actually if you look at this particular structure, the sixth structure which you see here, where the white and the yellow where the white and the black they are in the same plane. So this white and black will now be on the vertical line, and the one these two bonds, the yellow and the red, right, this will be on the horizontal axis. This is the way you can convert a Fischer projection, a wedge and dash structure into a Fischer projection. More I will try to tell you in the next video. Thanks for watching. Hope you liked my video, and if you liked it, please give it a like, comment and share it with your friends. Thanks for watching.